Hi. Okay, new lesson, new part of the periodic table. So, science o'clock means we're doing chemistry at the moment. Today we're looking at the noble gases. So we're moving on from the alkali metals and the halogens, but the starter still includes those things in it. So, to start off, name me 5 alkali metals. Write them down. 4 halogens. Also write those down. 3 salts. Tricky. Name 2 halogens that could replace the halogen in potassium bromide. And then for those two, so it says the balance. So write the balanced equation for one displacement reaction from the previous question. So the previous question is asking about a displacement reaction. Which halogen could cause a displacement reaction with potassium bromide? When you've chosen it, write it down as a balanced equation. Pause. Do it. Go. Sick. Right, okay, so I'm assuming you've done that. Let me check. Is the pen working? Pen. Pen. Splendid. Name 5 alkali metals. So hopefully lithium, sodium, potassium, okay, francium, and cesium. Nice. Name 4 halogens. Fluorine, chlorine, bromine, and iodine. Check. 3 salts. Salt is when you take a metal and a non-metal. Hint, I was asking for you to take an alkali metal and an halogen and put them together. So table salt, for example, is NaCl. But you could do any alkali metal and any halogen. So we can have lithium bromide. We could have potassium iodide, or any other combination. Metal, one of those, and one of these, followed by one of these. Nice. And you just need 1 on 1. It's a 1-on-1 relationship ratio. What are the 2 halogens that could displace the halogen in potassium bromide? So potassium bromide is KBr. The halogen is bromine. Which 2 halogens are more reactive than bromine? The 2 halogens that are more reactive are either chlorine or fluorine. And can you write the balance equation for one of those displacements? The balance equation, let's check I did this right. So 2KBr plus Cl, don't forget the 2 because chlorine is, and all halogens are diatomic, turns to 2KCl plus Br2. Check. Did you get that right? I'm so proud. Okay, so let's look at those halogens. No, not halogens, noble gases. Those were the halogens, but those noble gases over the end. They are on the right of the periodic table. They are classed as group 0. 0. Nothing. And they are helium, neon, argon, krypton, xenon, and radon. They all end in on, pardon. Helium. Heliumon? No, sorry. And here they are. Helium, the smallest, 4-2. Then neon, then argon, then krypton, then xenon, then radon. They're all fairly unreactive. In fact, there's not a lot to say about them in terms of chemistry, in terms of what they do. They've got a full outer shell. So they are like the chosen elements. They are the ones that don't need to lose or gain electrons to get a full outer shell. They are already complete. All other elements are jealous of them. Look at those noble gases with their full outer shell. How dare they go around flaunting their full shells, whilst the rest of us just lie around with not enough or too many electrons. So they are fine. They're not very reactive. So they don't want to attract electrons. They don't want to get rid of electrons. So they're really quite boring. They're unreactive. They're stable. Inert. Another word for unreactive. So nothing happens. They don't really bond with anything else. Why would they need to? They only form bonds if you want to get rid of electrons. They're fine. And because they don't form bonds, because they don't need any other electrons, they are monatomic, as in one. Mono, as in like a monobrow. If you have one eyebrow, you have a monobrow. And they are monatomic. They just need one atom to exist by themselves. Most other gases are diatomic. They are monatomic. They are fine. Pretty boring in the scheme of things. Not a lot to say. Unfortunately, there are a lot of slides, so there is a lot for me to say. They are colourless, odourless, and unreactive. So I'm just going to say how boring they are. They don't do anything. Yeah, they're so dull. They're colourless, odourless, unreactive. They don't do anything. You just put electricity, they don't care. Well, they do care a bit. But there are differences between them, and we're going to go over the differences. And then actually, their unreactivity makes them very useful. Oh. Here we go. So the density of noble gases increases as we go down the group. Here's a little animation to help you visualize this. So here we go. Density: helium 0.18 grams per decimeter cubed, neon 0.9 grams per decimeter cubed, argon 1.78, krypton 3.75, xenon 5.9, and radon 9.73. Now, if air is 1 gram per decimeter cubed, which of those will float? You know helium floats because helium balloons float. But what other ones will float? Is it just helium? How could you test this? You can't test it at home, I'm sorry, but how would you be able to test it? Let me show you. What you do is you were to collect some of these and... Oh, not working. Come on. Come on, sausage. Ah, there to it. Stop allowing me to select. Well, what you would do is you would fill them, put the gases into a balloon, but this is not allowing me to do it. And if you put it into a balloon, I'll leave this PowerPoint for you to do yourself. If you fill a balloon with helium, you know it floats. It floats quite quickly up to the sky. If you do the same with neon, neon also goes up to the sky, but slower because it's really close. Neon has a density of 0.9 and air has a density of 1, so they're really quite closely matched in density. So actually what happens is you put a neon balloon, it goes like that. Argon is more dense. That's still available on the other slide. Argon, there we go, argon 1.78, krypton 3.75 is more dense. If we were able to do argon, you would see argon falls down to the ground, probably as fast as neon goes up. Krypton and xenon actually quite heavy, so they would drop to the ground quite quickly, not as fast as like a tennis ball, but they would fall at relatively fast. You wouldn't do it with the radon because it's radioactive. That would be stupid, so don't do that. The boiling point, oh, come on. This is not working. I'll try with a pen. Yay! Perhaps could have done that with the other one. The boiling point, look at these boiling points. Helium is minus 269. It boils minus 269. The coldest temperature that you can reach anywhere in the universe is minus 273. So it's boiling at 4 degrees above absolute zero. That's boiling, so it bubbles and turns into a gas. You have to turn it down to minus 273 to get it to a liquid. That's not even a solid. That's insane. That is so cold. 4 degrees above the coldest temperature that can exist. Not known to man, that can ever exist. And even as we go down, the boiling point increases, but still minus 246, minus 168, minus 152, minus 107, and minus 62. So room temperature is about 20 degrees. So all of these will be a gas at 20 degrees. In fact, all of these will be a gas basically everywhere on Earth. Maybe radon. I think Antarctica has managed to get down to minus 88. So radon potentially could go to a liquid in Antarctica in the middle of winter, but that's an experiment I'm not willing to run. They are all have very low boiling points, but it does decrease as you increase as you go down the group. Okay, so I've talked about they're unreactive, they're boring, they don't need other electrons, they're monatomic. So why are they useful? It's their non-reactivity that makes them useful. The fact that they don't spark into flames and do bad things, that makes them useful. And in fact, you see them around you, maybe you just don't realize you see them around you a lot. So, for example, you know that helium floats. It's less dense than air. As a consequence, you can fill things with helium and they will float. A blimp balloons. Very good example. If you go deep sea diving, you're not going to do it at the moment, they put a small amount of helium in there. That helps your body. The bends is when your body, I believe it's when some of the nitrogen in the air that you don't do anything with goes into your bloodstream and it's bad. They put it in breathing and gas. Most importantly, I think helium nowadays is used in terms of like computing and other like reactions because it makes things really cold. In fact, as a planet, we are running out of helium, and it's really important. We need it, but you just can't find it around. So like high performance magnets, somewhere like the Large Hadron Collider uses helium because it needs to make things really cold. So it's used as a supercoolant. Neon is used. Neon lights, they're the lights that you see on shop windows and bars and pubs and roller discos and bowling alleys and things like that. What happens is if you put electricity through it, it glows. It's not a chemical reaction, it's just glowing. The electrons are jumping up. That's energy levels. It's used in lasers, or some lasers, and it's used as a cryogenic refrigerant when you want to make something really cold really quickly. Here's an example. This is probably some kind of frozen embryo when someone's had IVF. When someone's having IVF, they make multiple embryos and then they freeze some for use later. Cryogenic refrigerant, argon. So in old school filament lamp bulbs, the bulbs that, if you were to draw them, they look like this. Oh my gosh, that's like the worst type of. But you know what I mean. Inside them, they put those with argon, and then what happens is the electricity flows through this filament, and it gets really hot. It gets really hot and it glows. If there was like air in there, it would catch fire. That's not good. So it stops it from burning. You also, like neon, if you put electricity through it, it glows. So they're used in some of those energy efficient light bulbs, the ones that have the weird shapes. And there's a gas blanket for arc welding. Arc welding is a type of welding that uses kind of like high current electricity, and it makes these big sparks and it welds pieces of metal together. But with such a huge amount of heat involved, the oxygen in the air can cause a chemical reaction. If you have a layer of argon around the welding, it kind of, because it's heavy, it sinks, so it doesn't kind of float up, and it stops the air getting in, protecting the welding from reacting or oxidizing. Krypton is used for laser eye surgery to stop bleeding in the retina. Ooh, nice. In lighthouses and other types of lamps, xenon is used in electron tubes, lamps, photographer's flashes, and lasers. And radon is used to treat cancer because it's radioactive. Normally, the treatment for cancer is to give cancer and just hope that the cancer gets cancer faster than the person gets another cancer. It's crazy. So you don't want to do radon too much. It's very hazardous. Oh, near the end. Here we have some examples of some questions. Do all noble gases have 8 electrons in their outer shell? True or false? I'm not going to do this. The properties of noble gases made them difficult to discover. Noble gases are often used in lighting. All noble gases are less dense than air. Noble gases have a few uses because they're so unreactive. And noble gases are monatomic. Oh, go on, let's see the answers. Let's see if it allows me to do it. All noble gases have 8 electrons in their outer shell. False. But I told you they have a full outer shell. Helium. That's 2. Noble gases. The properties of noble gases make them difficult to discover. True. They don't react. They don't do anything. Noble gases are often used in lighting. It's true. I gave you more than one example of lighting. All noble gases are less dense than air. False. Some are more, some are less. Noble gases have few uses because they're so unreactive. False. Oh, false. They have multiple uses. All noble gases are monatomic. True, they are monatomic because they don't react. Did you get that right? Of course you did. You didn't do anything. I gave you the answers. But together, we got it right. Together, we're learning. Aha! Time for you to do things. It says task 2 there. You haven't really done anything else, so it's probably still task 1, apart from the starter. So, first thing, I'm not going to give you the answers. Draw the electronic structure for the first 3 noble gases, and label the numbers of protons and neutrons in each nucleus. Don't draw them, just label. Use your diagrams to explain why this group of elements is unreactive. So the first one is a drawing, and the second one is explaining why they don't react. Pause. Do it. Pause. Do it. Number 3. Describe the trend in boiling point down group 0. As you go down the periodic table, how does the boiling point change? Explain this trend in terms of the attractive forces between the particles. Ooh, that's going back to like the beginning of the GCSE. Why do things boil? When you're changing state, what's happening, and why is it easier for something to boil than something else? It's about those forces between the molecules or particles. Describe the trend in density going down the group. Oh my gosh, I said earlier the density of air is 1, but it says here the density of air is 1.2. Shame on me. Which noble gases will float and which would sink? And then explain the trend in density in terms of the relative mass of the atoms. Okay, so maybe if you go back to your question 1 where you've drawn them and you look at them, and then you can explain why helium is less dense than something else. Excellent. And the last thing. Table shows some of the uses of the gases. Here we have some uses of the gases. The last column is empty, so you need to copy this table down, and then you need to say why we use helium for party balloons and airships. Why do we use neon for advertising signs? Not why do we use it, what property of it makes it good? Okay, helium, why do we use it in party balloons? Maybe because it makes your voice go squeaky. That's pointless in an airship. What property of helium makes it good for party balloons and airships? Same for the advertising sign, and the same for argon. Okay? Excellent. I'll leave those to you. I'll give you the answers in another PowerPoint or lesson or something. Okay, love you. Bye.